roughly today, plus minus a billion years or 2 billion years, the universe is dark energy dominated, and we see a slight acceleration in the expansion of the universe. The pictures that I put down here are these. We have here inflation with its quantum fluctuations that we can calculate, and remember they are all virtual fluctuations. We don't consider any external observer there. And then there was the end of inflation, and the energy of the inflaton field went into the production of particles. Those particles then acted as observers and decohered what was previously quantum fluctuations. So we had actual fluctuations then in that gas. And this is symbolized here by this picture here. We just have a plasma of hydrogen, a plasma of protons and electrons. And then here, when the protons and electrons formed hydrogen and the photons were released, then we had what might be called a dark universe. The light was still traveling around, but there were no, it's called a dark period because there were no suns yet, no stars yet that would produce light. And then a few 100 million years in, actually surprisingly early, according to current observations, the first stars formed and the universe was illuminated by them, and that also led to some ionization. In any case, over the subsequent billions of years, the universe as we now know it formed by the condensation of this hydrogen gas into galaxies, clusters of galaxies, and within galaxies into stars. Okay, but the whole structure formation, the whole origin of inhomogeneities can be traced back to the quantum fluctuations in inflation. There may be extra sources of inhomogeneities, for example, so-called isocurvature fluctuations that might arise from phase transitions in that period, but they have a different statistics, and according to the latest summary of data that you can, by the way, always look up in the summary of the particle data group on the internet, they collect all the latest properties of the particles and cosmological models. According to that, the isocurvature fluctuations, in other words, inhomogeneities that do not originate in inflation, they could at most be something like 1 or 2% of the fluctuation. So it's not excluded, but they can't be the bulk of it. Yeah.
Yeah. So how do we, like if you look at those fluctuations of the quantum field, it's like we measured the whole thing, right? But when you decohere with an environment you don't have access to, like say gravitational degrees of freedom, say we don't measure them directly, right? We measure their effects on other quantum systems we got entangled with. You kind of get a preview of like the average, averaged over the unknown variable, right? You trace over the unknown variable, whereas here you collapsed it to a single outcome, and you see that. That's weird. So,
well, if you ask me if I can solve the measurement problem, no, nobody can. We don't know how the single instance is created in a measurement, right? And so all we can do, as far as the math is concerned, is that we can couple the gravitational inflaton degrees of freedom then to the freshly excited degrees of freedom of matter, and then with tracing we get pure states go into mixed states and all of that. It doesn't tell us the individual outcome. That's true. But we just have to, well, that's the status of the measurement problem. Nobody knows how the gambling actually takes place. Okay, so what are the actual observations? Remember, there were lots of photons crisscrossing the universe there, but they couldn't go very far because they struck individual protons, individual electrons, and they are charged, and so the photons don't have much of a mean free path. But after protons and electrons form neutral hydrogen, photons can travel far, and in fact they've been traveling since, and that light now looks like this. This is like a map of the world where you would have Australia here and Europe there, North America there, and so on, except that this is outwards rather than looking from above down. This is the sky. This would be the galactic equator here. And there have been subtractions of the galactic equator of this. To give an idea of how much radiation that is, I looked it up. It's about 411 cosmic microwave background photons per cubic centimeter. Right? So if you go out there in the open and you take 1 cubic centimeter, at any moment there are about 411 CMB photons in there. This corresponds to a temperature of 2.7255 Kelvin plus minus about 10 to the minus 5. In fact, we know the deviations much more accurately than we know the absolute value of it. That's because differential temperature measurements can be done with very, very high accuracy. Actually, one experiment I know of works this way. They have a camera whose pixels are superconductors. And they are either superconducting or in a normal state. And the slight difference that the CMB makes can make that go between superconducting and non-superconducting. And because it's a phase transition, it's a very steep slope. And that provides the enormous sensitivity that's needed for this. Another way of displaying this is to project it onto a sphere. And then that's how the CMB looks like. Again, that's actual data. If we zoom in, it looks like this. Now those white lines in there are actual measurements of the polarization in the cosmic microwave background. It's very, very slightly polarized only. The polarization is only about 1 part in a million, whereas the temperature fluctuations are about 1 part in 100,000. So this is an indication of a vector field living on top of the CMB, the vector field whose direction is indicating the polarization. In fact, those arrows don't have heads, right? Because if this is the polarization, you might as well say that is the polarization. So it's not exactly a vector field, but it's similar to it. And you can decompose it into its curl and into its gradient part. And we will talk later more about the significance of the curl part. Of course, we mentioned it already in previous lectures that this corresponds to the signature of the gravitational wave quantum fluctuations during inflation. Okay, so how do we do that? How do we do these calculations? Remember, we decomposed the inflaton field into its zero mode that doesn't depend on space. It's just constant in space, only has a time dependence. That's the bulk of the field, the bulk of the amplitude of the field. And we treat that part classically. And we solve then the classical equations of motion of overall gravity without space dependence, just time dependence, and that part of the inflaton field, plus a perturbation of the inflaton field that is space dependent. And we are assuming here for the purpose of our calculations that the space dependence is very small, that the phi of x and eta is very small. So this goes along with a similar assumption for the metric. We write the metric as an FRW metric that doesn't depend on space, only on time. We treat that classically. And the combination of this classical field and that classical metric has to obey the classical Klein-Gordon equation and the classical Einstein equation. And then the perturbation of the metric that is space-dependent is assumed to be small. This will be quantized along with that, and there's going to be some interactions between them. The metric fluctuations we decomposed into the FRW part, a part that can be expressed through scalar field perturbations, vector fields, and tensor fields. And here they are. They have various unknown, they have various variables in them. And then we discussed that after using gauge invariance, after using the freedom to choose coordinate systems, we obtain with just a few surviving, we just obtain a few surviving gauge invariant degrees of freedom in all of this, and the rest of the degrees of freedom that we had in the metric and in the inflaton field are just expressing the freedom of choosing coordinate system. So the gauge invariant actual physical degrees of freedom are the tensorial part of the metric, Hij, along with a certain combination of the scalar part of the metric, the function psi, and the perturbation of the inflaton field. And that was the so-called Mukhanov variable here, R of x and eta, which has a linear combination of this scalar nature component, this component of the metric which is of a scalar nature, and the perturbation of the inflaton field, along with this prefactor here. Then we can put this ansatz for the perturbations into the action and calculate the perturbed actions. Then we obtain the original action for the space-independent inflaton field, the original action for the space-independent metric. So that was just what you would do with an ordinary FRW model. But you also get an action for this degree of freedom, that degree of freedom. In fact, they combine. That's why the Mukhanov variable arises here. We get an action for this degree of freedom, for this gauge degree of freedom, a gauge invariant degree of freedom, and we get an action for that gauge invariant degree of freedom. And here are those two actions. Here's the action of the tensor field, of the pure tensor component, gauge invariant tensor component of the metric. And notice that this is exactly the kind of action that we have considered all throughout this course. The only difference here is really this prefactor, but that doesn't matter. And the fact that this is not a scalar field, but a tensorial field. Other than that, it's just exactly of the same type. We have a derivative of the field, and then the scale factor squared. This is how the action looks like in conformal time and co-moving space coordinates for a scalar field on a given curved background. And now we find that the truly tensorial gauge invariant component of the metric behaves exactly like that. In fact, each of its polarizations behaves exactly like that. And then we have the action of the Mukhanov variable, of this combination here, combination of what is intrinsic curvature and the inflaton field. And this action also has exactly the structure of a Klein-Gordon field on a background space-time. There's the derivative of the field, and then z squared. Z is like a. Z squared is like the a squared, except it's a slightly different function. Other than that, it's exactly the same structure, and therefore the same math goes through. The quantization works the same way as we did it all throughout this course. You need to keep in mind that the z is not exactly a, though. The z is a squared over a prime, phi naught prime eta, and we discussed in a previous lecture how come that we have this factor here, how come that we have that factor there. In a certain approximation, this behaves just like the a, but it will turn out quite crucially, to be quite crucial, as we will see today, that the z is not exactly the a. So let's keep in mind that the Mukhanov variable has a slightly different time dependence. So now if we were to use these actions and just went ahead and calculated the equations of motion, we would find friction terms, as we did earlier in the course. So to preempt that, so that we can use everything we've done so far, we do what we did previously too. We switch to a new set of variables, which differs from the old set of variables just by the scale factor. So, for example, for the scalar action, for the Mukhanov variables action, we would have a friction term. But if instead of using the variable r, we use the variable z times r, where z plays the same role as the scale factor would have, then the new variable u of x and eta will have an equation of motion without a friction term. So we can use everything that we've done in this course. The fact that by convention we put a minus sign here doesn't change the fact that the friction term will go away. After all, it's a linear differential equation that we get. The minus sign will drop out. Similarly, we take the tensor action, the gravitational waves, that is. We take their action, and in order to avoid the occurrence of a friction term in the equation of motion, we multiply the hij here, also with the scale factor, and in the case of the tensor field, it is really the scale factor. We also multiply with this factor here as a matter of convenience. It has to go somewhere, this factor, so we plug it in here. Since it's a linear differential equation, it doesn't change the fact that the now obtained new variable Pij will have an equation of motion without a friction term. It's further convenient to take these gravitational wave degrees of freedom and extract from them the true degrees of freedom, which is to say, we express the gravitational wave degrees of freedom as a linear combination of the two polarizations that are possible. Remember that the hij cannot be any arbitrary matrix. They are perturbations of the metric, so for example, they have to be symmetric. But there are way more conditions on the hij. Just like when you decompose a vector field in electromagnetism into its curl and gradient part, the curl part is not just some vector field, it's a vector field that obeys special conditions. It's divergence-free. And so similarly, the truly tensor part, hij, obeys certain conditions. If you remember, we had them on some slides a little way back. And as a consequence of all those conditions that are placed on the hij and therefore on the Pij, this is not just any arbitrary matrix. This is not just any 3x3 matrix. No, it contains only really 2 degrees of freedom for 2 polarizations. So we can choose epsilon ij basis polarization matrices and then express the Pij as a linear combination of these 2. So now it becomes obvious that explicit that in the gravitational waves you have only 2 polarization degrees of freedom. We denote them by the variable lambda, which can take the values 1 or 2 for 2 different polarization degrees of freedom. So now, after having changed variables by multiplying with the scale factors, or the z that plays the role of a scale factor, and exposing the 2 degrees of freedom in the gravitational waves by decomposing in polarizations, we obtain these frictionless equations of motion. It's just the usual Klein-Gordon equation for the gravitational wave degrees of freedom. Remember, these are the 2 polarizations of gravitational waves. The lambda runs from 1 to 2. It's exactly the usual Klein-Gordon equation, except we don't have a mass term. When we did the perturbation theory, the mass term, as it happens, ends up with the bulk degrees of freedom, the zero-mode degrees of freedom, the non-quantized degrees of freedom. If you can think of it this way, the mass doesn't depend on space, so it belongs to the zero mode. And the perturbations that we calculate for the Mukhanov variable and for the gravitational waves, they obey massless Klein-Gordon equations. So here we have a massless Klein-Gordon equation, and there for the Mukhanov variable we have a massless Klein-Gordon equation. Again, there's a slight difference between the z's and the a. But other than that, same equation of motion. Yep.
So the fact that, so you know how for the photon we require that is transverse. So hij is transverse because the degrees of gravitational degrees of freedom are massless.
Correct.
But I'm wondering where this transfer condition came from. Is something we impose from the symmetries of FRW, or is we impose it just because we know it's massless?
No, it has nothing to do with FRW. It's always the case that gravitational waves are transversal, and that is ultimately just because they travel at the speed of light. As soon as you give gravity a mass, then the gravitons would have a longitudinal degrees of freedom, FRW or not FRW. So it really comes from those conditions. Remember, you take the electromagnetic field, you decompose it into a curl and into a gradient, and then along with that, you find that the gradient part is curl-free, the curl part is divergence-free. And so similarly, if you do that for a tensor field, you get conditions. And one of them is that, for the massless case. There's actually something interesting to say about the appearance or non-appearance of a longitudinal degree of freedom. For example, you might ask, I'm going off on a little tangent here, but I hope you don't mind. In electromagnetism, when you calculate the Planck spectrum of heat radiation, then you find that every polarization of the electromagnetic field contributes equally. Obviously, they don't interact. The polarization, the longitudinal, let's say the horizontal and vertical polarization, if you decompose this way, those photons don't interact with each other. You can say that you have a part of the photon gas in a box that is this way polarized, another one that's that way polarized. So in other words, you have a factor of 2 in the Planck formula for heat radiation, which traces back exactly to the fact that photons have only 2 degrees of freedom, 2 polarization degrees of freedom. Now, what if the photon had a little mass? A tiny, 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 tiny little mass. Well, then it would have a longitudinal degree of freedom, and therefore the Planck formula for heat radiation in a box would have a factor 3, where it used to have a factor of 2. And that's totally measurable, right? It would mean that heat radiation is 50% stronger. So it would seem that we can tell by checking the Planck formula to experiment that the photons definitely don't have a mass. But can we really? See, the same applies to gravitons, of course, right? Or it's just much harder to measure the heat radiation, but as a matter of principle. Can we really tell that photons don't have a mass from this experiment? Actually, we cannot. We cannot, and the reason is that if photons had a longitudinal degree of freedom, if they had a tiny, tiny little mass, then that longitudinal degree of freedom couples to fermions with a vertex, with an interaction Hamiltonian that's proportional to the mass. And if the mass is very small, it means that this longitudinal degree of freedom would take a long time to equilibrate. So it's true that in the thermal equilibrium, you would have a factor of 3.5 compared to what you would have earlier, and the heat radiation would be 50% stronger. But you might have to wait longer than the age of the universe for the thermal equilibrium to kick in. So it's a general phenomenon that you may want to keep in mind also in other studies, that sometimes you have discontinuities in physics, apparent discontinuities, like give the photon a tiny mass. It could be arbitrarily small, and the Planck formula, bang, changes by 50%. And you might think, oh, that's great, I can make measurements. But somehow nature always manages, it seems, to soften the blow and to make us not be able to use that extreme sensitivity there. So we can't really be sure that the photons don't have a mass.
So it's related to the variance of an observable versus its change over time or whatever. Like the generalized energy time uncertainty to other operators, and then other observables or observable being maybe the mass. You're right that can come up as well. It could be that quantum fluctuations mask what would be classically a sharp transition, like a 50% increase in the radiation. But I think in this case, it's really classical noise that's masking it. It's the time it takes to classically equilibrate. But you're right, it could also be quantumly. Quantum mechanics could also mask such a sharp transition. Okay, but as far as standard theory is concerned, if you don't do major surgery to the theory, gravity really is having massless gravitational waves, and photons do too, and our perturbation of the infraton field do. Okay, so now we want to calculate the quantum fluctuations of all of this. As before, solving these Klein-Gordon equations reduces to solving the equations of motion for the mode functions.
right? So we express our field operators again in terms of A-Dagger operators multiplied with mode functions. And the A-Dagger operators take care of the commutation relations. The mode function's job is to take care of the equations of motion. And remember that the A-Dagger operators take properly care of the commutation relations between phi and pi if the so-called Wronskian condition is obeyed. So our mode functions have to obey two things. They have to obey the Klein-Gordon equations for the Mukhanov variable, for the gravitational waves, and they have to obey the corresponding Wronskian conditions, and then everything goes through as we always did in this course. So here are the equations of motion then for the mode functions. Let's call them U tilde, just to indicate that these are number-valued functions, as opposed to the ones with the hats, which were the operator-valued functions. So the U tilde and the V tilde are the mode functions, so they're complex number-valued functions of time for every k. They have to obey the Klein-Gordon equation. Remember, for the Mukhanov variable, it's really the z, not the a. And we have to set initial conditions for those mode equations. Well, let's look at what these equations of motions look like at early times. We will be interested in the extreme regimes, early time, very early time, and the very late time after the mode crosses the horizon. And at early time, we have that the k-squared term is dominant. And at late time, we have that this term is dominant. Remember, this is after horizon crossing. When this term becomes dominant, then this whole thing, this whole bracket changes sign. So when, at early times, sorry, at early times when the k-squared term is dominant, then we can look at the equation of motion without these, and what we have is just Minkowski space. It's just Minkowski space equation of motion. So we can set as the initial conditions the Minkowski space behavior of the mode functions. Of course, it's never exactly Minkowski space. So what you can do is you can go very far back in time, very early in time, when this term is dominant. It's not completely the only term, and you can apply the adiabatic vacuum identification criterion, and you get basically the same thing as choosing Minkowski space right away. And it's in practice, it's called the Bunch-Davies initial condition or vacuum condition. So then, what are the mode functions at late times? Well, at late times, the following will be happening. At late times, the mode k cross the Hubble horizon. Of course, not all modes make it, but the ones that we are interested in will have crossed the Hubble horizon. At late times, when inflation is late or has already ended, we have that the z double prime over z and a double prime over a terms dominate then. And the harmonic oscillator in the equations of motion, in the Klein-Gordon equations, will be inverted because those brackets changed sign. So therefore, instead of having two solutions to such a Klein-Gordon equation, which would be typically sine and cosine, or e to the power I omega t and e to the power of minus I omega t, doesn't matter, they're equivalent bases, right, sine and cosine, or e to the power I omega t and e to the power minus I omega t. Instead of having those two, which are legal basis vectors at early times, when it's basically Minkowski space, instead of those two at late times with the inverted harmonic oscillator, instead of having e to the power I omega t and e to the power minus I omega t, the omega becomes imaginary. And so you have an exponential growing solution and an exponentially decaying basis solution, just because the omega changes from being real to imaginary. So soon after horizon crossing, the mode function consists essentially only of the growing solution, right? So instead of having a positive frequency and a negative frequency basis solution, we now have an almost exponentially increasing and almost exponentially decreasing solution. And dominant will be, of course, the exponentially increasing solution. Remember, it doesn't mean that the actual mode function exponentially increases. It's just the new variable that we chose. Right? We have to go back to the physical variable by dividing by the scale factor, and then what we get is a mode function that actually freezes. Remember, physically, what happens is that when you have a wave that lives and oscillates on an expanding space-time, and its wavelength starts exceeding the size of the horizon, and it stops oscillating. Doesn't mean it grows its amplitude or anything. No, it just stops oscillating. It freezes. But mathematically, because we are not looking at the mode function itself, but the mode function rescaled by the scale factor, and the scale factor is almost exponentially increasing, right? So we have that the mode function that we actually work with is almost exponentially increasing. The physical mode function is what we obtain when we divide it by the scale factor, and that's the one that is just freezing its amplitude. Okay, now let's estimate what is the growing solution going to be at late times. I'm doing this to give you some intuition. I could just give you the solution. It's to do with hypergeometric functions, and we will do that in a moment. But let's just see beforehand what we should expect here. So the equations of motion after horizon crossing will have these terms dominant and the k-squared terms essentially negligible. I was already saying that, therefore, we expect that what used to be positive and negative frequency plane waves become exponentially increasing, exponentially decreasing solutions. Here is how we see that explicitly. So here's the Klein-Gordon equation. Assume this term dominates. Well, then we have u double prime plus minus z double prime over z, u equals 0, which we can also write in this way. Okay, it's just rewriting that equation. We can write it this way, which says that u double prime over u is equal to z double prime over z. And similarly, we can write the equation of motion for the gravity waves. And we obtain that in the limit of late time after horizon crossing, we have v double prime over v is a double prime over a, which means that they have to behave exactly the same way. So the u tilde has to be proportional to the z, and the v tilde has to be proportional to the a. Now, we are no longer doing de Sitter inflation. De Sitter inflation would be exponentially increasing, would be having an exponentially increasing scale factor. We're going to use a model that has a sub-exponential increase because we need this slow roll in inflation. So our scale factor a of eta and the related z of eta are not going to be exactly exponential. And so the v is not going to be exactly exponential, but almost. And of course, once we divide it then by a, it's going to be roughly constant. Namely, if we take, you see, u was the rescaled Mukhanov variable. It behaves like z of eta. But the actual Mukhanov variable, the gauge invariant degree of freedom, the gauge invariant scalar degree of freedom, is u tilde divided by the z of eta. Now, since the u tilde goes like z of eta, the ratio of the two goes to a constant, and the same argument can be made for the actual gravitational degrees of freedom, the gravitational waves. So both of them freeze after horizon crossing. And remember that what this is this famous phenomenon of, that is also called the amplification of quantum fluctuations due to inflation. And what it really means is that these mode functions, actually their modulus square, the modulus square of the mode functions gives you the size of the quantum fluctuations. Remember the calculation with the box and the 2-point functions and so on. The modulus of the mode functions gives you the size of the quantum fluctuations. And what this is saying is that the size of the quantum fluctuations to the mode k freezes, becomes constant after horizon crossing. So the quantum fluctuations are large for small wavelengths, and then they become smaller as the wavelength is increased. But as soon as you reach the Hubble scale, the modulus freezes and the quantum fluctuations stay the same size, even though the mode grows larger and larger. And this is how it can happen that at the end of inflation, a mode which at the end of inflation has a wavelength of supergalactic scales still has an amplitude in its mode function that would be appropriate for a mode, Minkowski space, it would be appropriate for a mode of a very, very small wavelength, like 10 to the minus 29 meters or so. So very large quantum fluctuations. So you can have at the end of inflation a mode of supergalactic scales, cosmological scales of wavelengths, which still has quantum fluctuations as large as ordinarily in Minkowski space only a mode of very, very, very small wavelengths could have. So that's how you can have the quantum fluctuations of a field, be it of the metric or of an inflaton field, can play a role at cosmological scales. Right, I think I just said this part. Okay, now remember the quantum fluctuations in, I'm just making more accurate what I said earlier. The size of the quantum fluctuations of, for example, the Mukhanov field, or the size of the quantum fluctuations of the gravitational waves, according to our formulas earlier, are given by the modulus of the mode function times k to the power 3/2, where k is the comoving momentum of the wave. Remember, we arrived at this result, at this relationship between the size of the quantum fluctuations and the modulus of the mode function in two ways. One way was to consider a box, average the field over the box, and calculate the standard deviation of the averaged field in that box. That's how we arrived at this, where k was 1 over L, L being the size of the box. And an alternative derivation was to calculate the two-point correlation function between fluctuations of the field here and fluctuations a length L away, where L is 1 over k. And again, we found that the size of the two-point function is related to the modulus of the wave function by a factor of k to the power 3/2. Okay, so the statement, just to say it again, because it's here on the slide, this quantity stays the same. The amount of quantum fluctuation stays the same for a mode after it crosses the horizon, even if it then goes on to get expanded to cosmological size. So our aim now is to calculate these the size of these quantum fluctuations, both for the gravitational waves and for the Mukhanov variable, in a scenario that is more realistic than the zeta inflation. So here's a realistic example: power law inflation. In fact, the experimental data are now so accurate that we know that it can't be exactly power law either. It has to be a little bit tweaked away from power law. But that's already a very good approximation. So what we need, the power law inflation has the advantage that we can still solve the Klein-Gordon equation exactly. Just like in the de Sitter case, we were able to use Bessel J and Bessel Y functions to solve the Klein-Gordon equation explicitly, and therefore to connect the initial conditions to the after-horizon crossing amplitudes. With power law inflation, we can also connect the initial conditions to the after-horizon crossing amplitudes, because we can solve the Klein-Gordon equation explicitly in terms of hypergeometric functions. Okay, so power law inflation, what's the idea there? The idea is that the universe didn't expand exponentially, but just with a very high power instead. We need an explicit potential that does it, an explicit inflaton potential that would do this very thing, so that we can then, a potential that will induce a scale factor that expands, that grows with a high power, and a corresponding inflaton field, a bulk field or zero mode field, constant in space field that goes along with that. A consistent joint solution of both the Einstein equation without space dependence and the Klein-Gordon equation without space dependence. So a consistent FRW model.
Again, we require power law for the conformal time? Power law equations?
We will have to recalculate what conformal time is, because the conformal time is calculated from proper time using the scale factor. So we will have to recalculate what the conformal time is.
So this power law, we require that A is a power law in
proper time.
Proper time.
Yeah,
right?
yeah. Right. Let me also remind you why de Sitter inflation is ruled out. Remember that when we use de Sitter inflation, the Mukhanov variable doesn't make sense. It would diverge, because the Mukhanov variable has this factor in it. Where is it? Here, that's the Mukhanov variable. And what it has is the inflaton perturbation, the scalar perturbation of the metric, but it also has 1 over phi naught prime. But you see, if the inflaton field doesn't change, because you see, constant potential means, de Sitter inflation means constant acceleration, means constant potential, means constant inflaton field, means constant phi naught, means phi naught prime is 0. 1 over that is infinite. So the Mukhanov variable doesn't make sense. We can only use this variable if the universe is not expanding exponentially, but significantly sub-exponentially. Also, I should stress that the Mukhanov variable is only gauge invariant perturbatively. Nobody has managed to do this non-perturbatively. So only if we have perturbations that are of first order is this really a gauge invariant quantity. And by that I mean, how you choose your space-like how you foliate your space-time into space-like hypersurfaces. Yeah.
So this is, this whole technique is how to split into classical and quantum fluctuation part. And you're saying that if we try to do quantum cosmology for the de Sitter universe, then it's like basically full quantum gravity, or like we can't do this.
No, I give you some more intuition for what it would be if we did inflation, in de Sitter inflation. I actually have a nice picture for it too. And I hope that the picture will say more than 1,000 words. Yeah?
There is also a problem with the Sitter inflation that you cannot exceed to a Feynman universe after. Because at some point you want your universe to start this.
Well, true, but power law inflation also, has to be forced to end. Yeah, it's true that if in de Sitter inflation, if phi dot was 0, right, which is what it would mean, then phi would never reach a new region in the potential where it could then drop down and end inflation. With power law, you have slow rolls, so it could slowly roll down a hill, and then eventually it falls off a cliff, and inflation ends. Okay, so what we need is a potential that does the trick, that gives us power law inflation, which is a power in proper time. The scale factor increases as a large power in proper time. Proper time of an observer that freely floats with the Hubble expansion without peculiar velocity. Now, de Sitter is ruled out, as we just discussed. We need slow roll. And we can parameterize this slow roll. The idea is this: we do not know exactly how the potential of the inflaton field looks like, but we can parameterize it, it is as if we were Taylor expanding it. And then, based on measurements, we hope to nail down what the Taylor coefficients are, and from that, determine, therefore, how the inflaton potential looks like. Really, the only thing we can really measure about it is, of course, the actual slow roll period. We don't know how the potential goes on previously or how it goes on after the dip where the reheating happens. But we can at least try to get the slow roll to some accuracy. So we would like to know what is the slope, perhaps what is the second derivative, perhaps what is the third derivative, and so on. So for all values of phi naught, so here's the potential as a function, inflaton potential as a function of phi naught. And remember, it's phi naught because the overall expansion of the universe is driven by the classical Einstein equation for FRW and the classical Klein-Gordon equation for the phi naught field. No space dependence, the quantum fluctuations are just small perturbations around that. So for all values of the bulk field phi naught during the inflationary period, we can parameterize the slope here by its derivatives. And these are the so-called slow roll parameters. And by the way, remember that the potential V directly translates through the Einstein equation into the Hubble parameter. Namely, H is the square root of V. So whether we talk about the slope of V or the slope of the Hubble parameter is really the same thing. So here are the slow roll parameters as they are used in the literature. Unfortunately, the literature is not entirely consistent about this, but I would say most authors use these so-called slow roll parameters. So there's the epsilon of phi slow roll parameter, which is basically the first derivative. It's usually expressed in terms of h, the size of the Hubble horizon. But of course, ultimately, we are thinking about the potential. So you can also re-express this in terms of the potential. And then this is what you get. Then there's the second slow roll parameter. You could express all of this also in terms of the potential, the third slow roll parameter. But then, you know, how good are our data? Can we really measure them? Now, the simplest solvable case is the one where, remember, we have not specialized the power law inflation at this point. We've just parameterized how V changes with phi. And the simplest case for a slow roll scenario is that the epsilon is a constant. That the first slow roll parameter is simply a constant. So that this epsilon, the h prime over a, is a constant. And let's see what we get when we do that. So we have that epsilon is a constant. And epsilon of phi was defined as this quantity here that parameterizes the slope. Now, you can solve that for h, and then you find that h of phi is given by this exponential law here. So in order to have this first slow roll parameter constant, independent of phi that is, the h of phi has to have this value, and that means that the v of phi, which is basically the square of it, has this value here. And I leave it to you as an exercise to find out what that coefficient is. Also, it's a bit of a trap. Some people think that, you know, such as the source of confusion here, the v is the square of the h. So you might think that, therefore, the v of phi goes like a Gaussian e to the power phi squared, but of course not, because if you square it, you just get a factor of 2 over there. So what we have is that if the first slow roll parameter is constant, then the potential as a function of phi is exponential. Let's see, what does that further mean? It also means that the other slow roll parameters that we defined above, eta and psi, are also constant and agree with the value of epsilon. That's just by the way that we defined those slow roll parameters. And as it happens, the exponential expansion rate of de Sitter has now become a polynomial expansion rate. You can show that by just going into the FRW equations of motion. You find that if the first slow roll and all the other slow roll parameters are all constant, the potential is exponential. We have that the scale factor grows polynomially with respect to the proper time, where we have this constant c here. So if the slow roll parameter is very small, then the universe expands with a large power, right? So if c is very small, like 1/1,000,000, then you would have here t to the power 1,000,000. What does the small c mean again? Well, small c means, here we have the c. If the c is small, then the h prime over h is small. Okay, so that means small slope. Small slope means small c means large expansion. That doesn't mean that there's a smooth limit to the exponential, right? So it's not the case that as c goes smaller and smaller, suddenly this becomes an exponential, right? Even though the potential that we get, the slow roll parameter tells us that the slope becomes flatter and flatter, so it looks more and more like de Sitter in that sense, but it's never quite de Sitter because no matter how high that power is, even t to the power of 10 million is not behaving like an exponential. So it's again one of those cases where it looks like you have some sort of non-smooth limit happening, and as far as we can tell, it might even be a non-smooth limit. Also, we now have to recalculate what the conformal time is. Remember, conformal time is very convenient to use, but conformal time is related non-trivially to proper time. It involves an integral. If you go back to the old formulas, and if you carry out that integral, you find that the conformal time is now such that the scale factor as a function of conformal time is given by -1 over eta h, which would be the de Sitter formula, but multiplied with 1 over 1 minus epsilon. And you see again that there's a bit of a modification here relative to de Sitter. It's just this thing here. If epsilon goes to 0, it becomes ordinary de Sitter's conformal time.
So we have a smooth limit in conformal time.
As far as conformal time is concerned, yes. Yes. But not as far as the expansion is concerned. And for example, this has the starting time. De Sitter inflation doesn't. Right? This has a singularity it has the universe going down to 0 size at a finite time, at t equals 0, right? And that wouldn't be the case for de Sitter. So it's really a very different space-time. But still, because this is just some constant in front of the conformal time, the overall behavior of conformal time is still the same. Namely, conformal time is always negative. Past infinity is negative infinity. And future infinity is 0. So as conformal time approaches 0 from the left, sorry, from your perspective, approaches 0 from the left, then you drive towards future infinity. So then what are the mode equations? Now that we have an explicit model for our FRW, power law, we can now calculate in particular this factor z of eta that goes into the evolution of the Mukhanov variable. Remember, it's always a squared over a prime times phi naught prime. We can now plug in what our a is, the power law namely, and calculate what the z of eta is. And in particular, we can calculate what the z double prime over z is, because that's the crucial term that appears in the Klein-Gordon equation for the Mukhanov variable. And what we find, it's a little tedious to plug it in, but it's totally straightforward. What we find is that the z double prime over z becomes this expression here, nu squared minus a quarter over eta squared, where the nu is 3/2 plus c over 1 minus c. Again, as far as this is concerned, smooth limit to de Sitter as c goes to 0, and we would approach de Sitter in that sense, in the sense that the potential becomes flat, it's no longer rolling down, it's totally flat. In that case, this just becomes a 3/2, and then we have a 9/4 minus a quarter, that's 8/4, that's 2. And if you remember from de Sitter inflation, it was just k squared minus 2 over eta squared. So it's just slightly different. Now it turns out that this differential equation is known in the mathematical literature. It's called the Bessel differential equation. And the nu is the order parameter for the Bessel differential equation. And here's the solution. It's a little messy, but that's what it is. It's square root of 2, square root of pi half, and then you have this factor here, which looks complicated, but it's just a constant, right? You just have here the nu, and then pi half. If nu is 3/2, then it's just 2 pi half. It's just e to the power I pi is minus 1. So it's just almost minus 1. It's just a constant here. It looks complicated, but nothing dangerous there. And then we have here a factor of minus eta to the power 1/2. Never mind, you don't have to take the square root of a negative number here. It's not going to be imaginary because eta is conformal time, which is always negative. So you take the square root of a positive value here. And then you have here a so-called Hankel function of first type. Isn't it good that some people care about ordinary differential equations enough to work out those solutions for us? Okay, so that is great stuff because it means that we can solve the Klein-Gordon equation all the way. In fact, of course, there are two solutions, two basis solutions there, but I've printed for you here the solution that matches the initial conditions. If you go to early time, this just becomes e to the power of I omega t. So this is the mode solution that obeys the right initial condition and the Wronskian condition at early times, and therefore gives us the mode solution at late times.
I don't quite remember my undergrad quantum mechanics, but do these functions arise as like solutions in a certain setting to the Schrodinger equation, if I remember, or is that, I don't know if there's a bunch of functions.
Well, yeah, I mean, if you have a Schrodinger equation that looks like this, let's say if this were a second space derivative, yeah, right, for Hamiltonian, and then you would have a potential that has that kind, you could cook up a Schrodinger potential that would have that as a solution. But of course, this here is time evolution, not the eigenfunctions to a fixed Hamiltonian. Okay, so that's the full solution for the Mukhanov variables mode function. Let's look what its behavior is after horizon crossing. Oh, we still have, remember, we still have to multiply with, we still have to divide by the scale factor. So we still have to divide by z to get the actual Mukhanov variable r. This is the solution without a friction term, right? So now let's look at what this thing does after horizon crossing. So after horizon crossing, the behavior of this Hankel function is such that this is what you get. So this is just carried forward factors, and then we get constants to do with the gamma function, and then this overall behavior here, where nu, remember, would be 3/2 if it were de Sitter, but it's not quite 3/2 because epsilon is not quite 0. So in other words, if this were 3/2, then it was minus 3/2 plus 1/2, so it's minus 1. So it's not quite minus 1 in the case of power law. So if we translate that now into the quantum fluctuations of the Mukhanov variable, the thing that would have imprinted, these quantum fluctuations imprinted themselves at reheating into the space-time, leading to a Doppler shift, a Doppler blue shift, not Doppler, a gravitational blue, a gravitational red shift from photons that had to climb out of potential wells or come down from potential hills. These fluctuations after horizon crossing come out to be then of this size. But where what we've done here is to divide that solution after horizon crossing by the z. Okay? And because of that, we obtain here prefactors stuff, but very importantly also h squared over h prime. That originated in the fact that we had to divide it also by the z. Now, that is there's a crucial outcome here. This formula allows us to make a prediction for the size of the quantum fluctuations of the Mukhanov variable that would have imprinted themselves as temperature fluctuations on the CMB. But in order to really make a prediction, notice that we need to know h prime, not just h, we need to know h prime. Or actually, we need to know the ratio of h squared over h prime. So in particular, we need to know how high the energy scale is of inflation, and we need to know how slow the slow roll was. Both of which we don't really know. So that is a little bit of an unsatisfactory state of affairs. On one hand, we obtain here a crucial prediction, which is that we don't really have any k-dependence in this. It's very important. Other models for the origin of quantum fluctuations would have a k-dependence in this, but we don't have that. We have a so-called flat spectrum. But how large these quantum fluctuations are, that is something that we can only answer really, we can really only predict it if we know what h is and what h prime is. Or turn it the other way around. The fact that a flat fluctuation spectrum, when put into the plasma physics of the period when there were these reverberations in the plasma, leads to a fluctuation spectrum in the CMB that's very close to what we observe, makes us believe that inflation is right. And then we can use the measurement of this to determine how big that is. So we've not predicted h squared over h prime. We cannot, from looking at the CMB, tell how big h is. We cannot, from looking at the CMB, tell whether, h, remember, is the Hubble radius during inflation. We cannot tell whether it was small or large from measuring those quantum fluctuations. Cannot really tell at what energy scale inflation really happened. Because h, remember, is related to v, the potential, by square root. So we don't really know from measuring those temperature fluctuations how big that is. And also, we don't know how big the slope of the potential or the slope of the Hubble parameter is. We can only measure that ratio. Now, I invite you to, of course, plug in divide by z, plug in what z is, to verify that from here to there, we did that right. Now, let's look at the prediction for the gravitational waves. And you will see why it is so important to measure the gravitational waves, and why it would have been such a big deal if BICEP 2 had found them conclusively. Okay, I wanted to give you some more intuition first, though. Remember, well, let me give you some intuition for why the size of the quantum fluctuations would actually be divergent if the potential did not have a slow roll, if it was flat. You see, if it were de Sitter, h prime would be 0, right? V is constant, therefore h is constant, and therefore this thing would be 0, and the whole thing blows up. And we discussed about this earlier, and Guillaume, you had a question about it. So let me give you some intuition for why we have this extreme sensitivity of the size of the fluctuations of the Mukhanov variable with respect to how slow the slow roll is. So remember earlier in the course when we calculated the quantum fluctuations for a Klein-Gordon field living on a fixed background.
Just a small question. So you said we can measure h. We cannot measure h, and we cannot measure h prime, but we can measure the
H squared over H prime.
Yeah,
yes.
But if we can measure that, like, can we not like sort of solve a differential equation and get what h is?
Yeah, if you had a range, if you had, that's right. I mean, in principle, you're right. If you can measure it with some k dependence or something, yeah, you might. But we are not that accurate just yet.
Okay.
Kim?
So that ratio h over h prime, whatever, is measured at horizon crossing. But isn't that dependent on the k's and like?
Yes, well, that's right. Yes, and the same question. Over time, that changes because h is no longer a constant because of the slow roll. So in principle, if you can measure how this thing changes with k, so if the quantum fluctuations are actually not, see, if you could measure that slope, you could measure how that changes, then, you see, I mean, there's no explicit k dependence in there, but there's implicit because that would be, right? Yeah. Okay, so remember that previously in this course, we had found a very different result. Namely, if we just took a scalar field that comes along on a ride on a space-time, it's not interacting with it. Space-time is just doing its own thing. It's expanding some way, let's say de Sitter, and then we calculated what the size of the fluctuations were, and we found that the size of the fluctuations was just proportional to h, not to h squared over h prime. So for the Mukhanov variable, we now find this behavior rather than that. Now, why would that be? Remember that the Mukhanov variable is a slicing-independent combination of the scalar part of the metric and of the inflaton field. And now, the slower the slow roll is, the more dramatic is the effect of this gauge equivalence. Remember what it means is that the fact that the Mukhanov variable is gauge independent means that it is independent of the way you slice your space-time into space-like hypersurfaces. Now, if you have a universe that has a slow roll, then what you have is that if you want, you can slice your space-time in such a way that you always go around fluctuations of the inflaton field, such that the inflaton field on your space-like hypersurfaces is constant, in which case you don't have fluctuations in the inflaton field, but then you see along those space-like hypersurfaces that there are fluctuations in the intrinsic curvature. Or alternatively, you can slice your space-time into space-like hypersurfaces such that you go around the bumps in intrinsic curvature, in which case on those space-like hypersurfaces, the intrinsic curvature scalar is a constant, but then you see fluctuations in the inflaton field. And you can go between those two, but how much will they be different? How much will the two ways of slicing space-time into space-like hypersurfaces, how much will they differ? Now, when the slow roll is not so slow, if it's fast, then it will be very easy to change from one slicing to another slicing, because you can easily tell if I just change the slicing a little bit, the phi will have changed a lot. You see, because fast roll means the phi changes quickly. So you can make up for fluctuations in phi very quickly. You don't have to go huge detours to make up for the fluctuations of phi. But if the slow roll is very slow, then you may have to wait for quite a while to make up for a change in phi. So you may have to make larger detours. And that's why when the slow roll becomes very slow, then the statement that the Mukhanov variable is a gauge invariant quantity, becomes more and more shaky, because you would have to go huge detours to still make it to have the equivalence of either constant phi or constant intrinsic curvature. And I'd like to show you a picture that is meant to illustrate that. Here's a river flowing in a plane, and if that plane had a strong slope, that river would go pretty much straight. And the smaller the slope of a river is, the more the river is going to meander. And so it's similar in the case of inflation, where the slower the slow roll is, the more meandering, you can imagine, is the phi field doing relative to the intrinsic curvature. And eventually, for the de Sitter case, it would get completely out of hand because it would be completely flat. It's like a river that has no reason to flow anywhere. Okay, so remember the timeline as we discussed earlier. So we are calculating this part, and each mode has a horizon crossing somewhere in here. And then after horizon crossing, its amplitude stays constant all the way up until the reheating when inflation ends. And most modes will be very large at that point already, while keeping their mode functions modulus as large as it was when it crossed the horizon and was a very small length. Okay, so what we did is we calculated this delta Rk here at horizon crossing, and for every mode it's somewhere in here, and then the delta Rk stays the same, stays constant after horizon crossing up until reheating. And here we have observations, for example, by WMAP and some other collaborations of the cosmic microwave background, actual data there. Okay, so the idea is that, I think I said all these things already, the delta Rk imprinted themselves as intrinsic curvature fluctuations at the end of inflation. Do you remember why it was that the delta Rk didn't imprint themselves as fluctuations in phi? They imprinted themselves as fluctuations in the intrinsic curvature. You see, in here, it's gauge equivalent to speak of the one or the other, but not at reheating. And that's because reheating happens when phi goes to 0. It happens when the potential of phi goes to 0. So the reheating itself, the end of inflation, is triggered by phi. So it's the end of inflation happens on an equal phi surface, which means that any fluctuations that are there then are fluctuations in the intrinsic curvature, which is why the temperature fluctuations that we see come about because of fluctuations in the curvature, where you have to have the photons traveling out of gravitational wells or down from gravitational hills. I'm simplifying a little bit because there's a lot of plasma physics between here and there, but it's understood plasma physics. So here's the best fit today. And again, I took those data from the publications of the particle data group. If you just go online and check particle data group, you will find very nice summaries of standard model physics, and it's both standard model of particle physics and of cosmology. I think the particle data group is the most cited entity anywhere because it's the reference for what we know in physics experimentally. Anyway, so what we see here is a plot that shows here in this direction the multiple moments. It's like the Fourier decomposition of the sky, of the cosmic microwave background, but instead of Fourier, we are decomposing into spherical harmonics, because it's not R3, it's really a sphere that we see. So this is the decomposition into spherical harmonics. To the left, we have the low spherical harmonics, which are slowly varying functions. The spherical harmonics play the role of plane waves. So these are large angles, and these are very small angles over here. And here we have the size of the temperature fluctuations. They're all of the order of about 10 to the minus 5. I mean, this is about 10 to the minus 5 parts in 1 in temperature. Right, and what you see here is that theory and experiment match very, very closely. These different colored dots are experimental data from those experiments, the Planck satellite, the WMAP satellite, the Atacama Cosmology telescope in South America, and the South Pole telescope, SPT, and you see they very nicely agree with this curve. Now, it's not like you could have predicted this curve exactly like that 30 years ago. In fact, there is some parameter fitting going into this. And here are the key parameters that go into this. That the curvature, the overall curvature of space-time of our universe is 0. That it is the spatial curvature, it's basically spatially flat. That goes into this prediction of the continuous line here. Continuous line is theory. Also goes in, what also goes into it is the fit that the amount of cosmological constants, the contribution of the cosmological constant to the overall density of energy in the universe is 70%. You see, if the curvature of the universe is spatially 0, it means that the mass density is critical, and the cosmological constant has to account for 70% of all energy density in the universe. Matter has to contribute 30%, obviously, then, of which 90% are dark matter and about 10% are visible matter. And the cosmic microwave background itself contributes about 1 part in 100,000 to the critical energy density of the universe. So the CMB itself doesn't carry that much energy. It's only 10 to the minus 5 of the overall energy density in the universe. And by the way, we can also read off from the left end of the spectrum here how much we are moving against the CMB. The CMB basically defines the rest frame for the universe, and we are moving against that at the speed of about 370 kilometers per second. So it takes only about 1/3 of a second from here to Toronto relative to the CMB. We are that fast. Actually, our local galactic group is about twice as fast. We are moving relative to that in opposite direction. You see large error bars on the left, but the large error bars on the left are mostly because of unavoidable bad statistics. Because when we are looking at fluctuations on large angles, well, we just have one sphere of the CMB available, so we can measure fluctuations on large angular scales with much less statistics than those fluctuations at small angular scales. So this, in order to bring that error bar down, or those error bars down, we would have to travel halfway across the universe, take a snapshot of the CMB there, so that we have fresh data for the large angles. Okay, but you see, it's a tremendous fit here. It should be said, though, that most of this structure comes from the plasma physics. That is between the imprinting of fluctuations at the end of inflation and the freeing of the CMB photons. So basically, these are literally reverberations of the original quantum fluctuations in that hot plasma. But then let's look at the tensor modes. What are the predictions there? Well, we now have, for the tensor modes, for the gravitational waves, we have a usual Klein-Gordon equation, and we obtain for the A double prime over A in the case of power law inflation this expression here, which we can then simplify, and it comes out to be this. We can solve that equation of motion with, again, a Hankel function. And if we plug in all the scale factors and so on, everything we fixed to fix the power law, then we obtain this prediction for the size of the fluctuations of gravitational waves. Gravitational waves should have left an imprint in the polarization of the CMB. Here's again, this picture of a small part of the CMB, superimposed our polarization measurements. And the crucial thing I want to bring your attention to is that the size of the tensor fluctuations, therefore the size of the polarization fluctuations in the CMB, is predicted by inflation to be proportional to h. Okay? That's because the Klein-Gordon equation for the tensor waves, for the gravitational waves, has just a as the scale factor, a the scale factor itself. So therefore, our old calculations in this course apply one-to-one, and we get, as we did earlier, that the size of the fluctuations is simply proportional to the Hubble parameter. So what that means is that if we could measure how big the gravitational waves are, we would know the energy scale of inflation. We would know how big the Hubble parameter was during inflation. Therefore, just have to take a square root. We would know what, or just square it, we would know what the potential was during inflation. But remember, if we know h, we also know then what h prime is, because we've already measured the ratio h squared over h prime by measuring the temperature fluctuations. So in other words, if we can measure h, we can also determine what h prime is. And that means that we get a consistency condition. We get that certain relations must hold between the size of the tensor fluctuations, if hopefully we measure them, and the slope of the slow roll. And inflation predicts a particular relationship between them. Which means that if we could measure the gravitational waves, not only would it be fantastic because we measure gravitational waves of a quantum origin, but also we would learn at what energy scale inflation really took place instead of having an educated guess. And we could check inflationary theory itself by checking whether that relationship between the slope h prime and h is actually there or not. And at that moment, when people measure the h and have some indication as to the slope of the slow roll, then we can check inflation itself, and at that point, I think inflation becomes a theory that will last. At the moment, people are still working to challenge the theory itself, but that is a firm prediction, the relationship between h and h prime, and the relationship between the amplitudes of the temperature fluctuations and the polarization fluctuations. Well, we'll see. There's a huge effort underway now to measure the polarization fluctuations. As you may remember, BICEP2 in 2014 claimed to have measured the polarization fluctuations, and they were relatively large, right? Which meant that the energy scale of inflation was relatively large, and there was a huge excitement about it. But apparently, all that was seen there was really foreground from the galaxy. See, foreground between us and the CMB can turn fluctuations of a non-tensorial kind into polarization factorial, can turn polarization fluctuations or just temperature fluctuations into polarization fluctuations, even of a tensor kind, if one is a bit unfortunate, and apparently we were with the BICEP2. But there's a whole range of experiments now that try to measure the so-called B-polarization, the curl part, the part that is sourced by the gravitational waves. So let's hope that that will be done, and then we have a much better picture, and hopefully, well, maybe hopefully we will not confirm inflation, because then we will learn the most. Right, I think Guillaume, you were first.
Yeah, so, I mean, if there's something kind of hiding our view, we could just move around a little if we could, and then see the background versus the foreground, be able to isolate that. So have they thought, maybe?
Well, actually, yes, there are some very clever ideas around there. For example, I mean, roughly speaking, we would like to see the CMB not only here, we would also see it some other place, because then we could have information about the lower angular modes. Maybe we see some sort of reflection of the CMB elsewhere. Roughly speaking, I mean, we are not going to see really a mirror far away, but the CMB has impact on various phenomena in astrophysics, and you could observe those phenomena elsewhere and measure thereby how they were influenced by the CMB there. And so it may be possible to measure things in indirect ways in this way.
I'm saying not even on that scale. Just even if you have a reflection in a glass and you take a picture, if you move around, there's algorithms to isolate the reflection from the background.
Yeah, but our angular, like anything within the solar system on a cosmological scale is going to be so small angular shifts that.
Well, no, it's just like the stars and the dust within our galaxy we're trying to.
Yes, but the orbit of Earth around the Sun is really tiny compared to the galaxy.
Voyager type thing, like 50-year mission.
Yeah, but even then, you see, the galaxy is hundreds of thousands of light years across.
Yeah.
Light years, and our solar system is like a light day. So it's one light day compared to hundreds of thousands of light years, and that is like 1 part in 10 million or 1 part in 100 million, roughly speaking. So yeah, I mean, who knows? I mean, we've done measurements with more digits behind the comma. Whether these are of the kind that we can do with this precision, I don't know. But you're right. Ultimately, we have to think outside the box and outside the galaxy box. Yes.
So, since there's mechanisms that change temperature fluctuations into tensorial fluctuations, how do we account for those?
Well, we can't really do that very well. First of all, there are primarily temperature fluctuations are going to trigger polarization fluctuations in a big way, but mostly it's going to be of the gradient kind, not of the curl kind.
No, less so for the tensorial observations, more so for, say, Planck data looking at temperature fluctuations. How are we accounting for some of that fluctuations being affected by galactic or intergalactic medium?
Well, you just have to write the bullet there, and it's very dirty physics. I mean, there's so many phenomena that can be in the way, and you just have to hope that you're not overlooking something. You have to first identify what could be in the way, and then model it correctly, and estimate the errors in that. It's very, very difficult. Yeah, very difficult, but it employs a lot of people to do this, and it's very much valuable to do it, of course. Was another question, no? Answered? Great. All right. Okay.
One more question. So in the spectrum for the gravitational waves, you have a square root of epsilon, right?
In the spectrum for gravitational waves, you have the square root of epsilon.
Yeah, there, like the box.
Yes. Where's the square root of epsilon? No, that's a G. That's a G. It's a gravitational constant. Sorry.
Okay.
No. Yeah, that would mean that it goes away with. No. Right. Yes. Yeah, so the gravitational wave, the amplitude, remember, doesn't depend on how slow this is rolling, right? It depends a lot for the Mukhanov variable and therefore for the size of the temperature fluctuations, crucially so. Could even be divergent if it isn't slow rolling at all, right? But for the gravitational wave spectrum, for the polarizations, no, it's just straight, the scale of the horizon. Yeah.
And so also following on the question I asked earlier, if we have a lot of those calculations done that kind of estimate how much temperature fluctuation is going to lead into tensorial things, does that give us a vague idea of what kind of the background should look like in any given direction? Or like the foreground, I guess, should look like in any given direction when we start looking into?
I'm not sure if I understand your question entirely, but one thing is for sure, you can use the CMB as a diagnostic tool. So it's not only that you try to find out about the CMB, you can also say, I know that much about the CMB. It goes through this much material, and then it's like an X-ray you take of the universe.
That's what people usually do.
Yeah. So you can use it also, it goes both ways.
Yeah, on the other hand, like foregrounds that affect like small angles. So you know pretty well what is going on at like large angles.
Yeah.
Yeah.
You have all the foregrounds.
Yeah. Yeah.
Right.
I guess yeah, most of that stuff would be in the smaller.
I mean, yeah.
Yeah.
Like most microwave sources are not going to be fractions of a degree.
Yeah.
Yeah, this, by the way, the peak here is at about the angular size of the moon. So if you saw the CMB on the sky, if your eyes could see the CMB, if it was sensitive to, it's temperature radiation. It's very cold now. It's only 2.7 Kelvin, even though it started out at 3,000 Kelvin. If you could actually see it, you would see that the most prominent fluctuations would be of the size of the moon. Somebody produced a picture, actually, of how that would look like, superimposed on some landscape and the moon and so on. Right. Okay, well, see you on Friday.